Welcome to the lecture on Chapter 19 for PTAC 2314, Principles of Quality at San Jacinto College. The topic for Chapter 19 is process capability. Process capability is a measure that indicates whether a process can meet product specifications and how effectively it can meet those specifications. Processes consist of the people, materials, machines, and methods used to create a product. Process capability and statistical process control. Often process capability is indicated by the Process Capability Index, CP. With process capability, companies will link the statistical process control, or SPC, to the specifications set for the process and the product. In essence, process capability and SPC are addressing the question of whether the process is doing what it is supposed to do. The value CP, Capability Index, determines the relationship between engineering specifications and statistical requirements. Mathematically, the formula is CP equals USL minus LSL divided by 6 sigma. Recall that in the normal distribution, review Chapter 17 for more information on that normal distribution, we found that 99.7% of variation was between minus 3 sigma and plus 3 sigma. The distance between these values then is 6 sigma. Therefore, we measure the ratio of the specified limits of the process and the normal spread of variation inherent in the process with capability index. Similar to the control levels described in earlier chapters, the upper specification limit, USL, and lower specification level, LSL, are established to ensure that the products provided to external customers meet a particular quality level. These specifications are often mentioned in the sales contracts for the product so that customers can be guaranteed an expected range of quality for the products they purchase. For example, if you are a chef purchasing a spice to add to ground beef for specialty hamburgers, you would want to know that the spice contains between 1 and 2 tablespoons of salt per pound. These would be the lower and upper specification limits respectively on the spice that you purchase from a vendor. If the spice had 3 tablespoons of salt per pound, the chef will end up serving an overly salty dish and his subsequent customers would be unhappy. Because the salt level is important in this example, the spice manufacturer will specify in their sales contract that the salt content will vary between 1 and 2 tablespoons of salt per pound. Components of process capability. There are 3 primary components to process capability. 1, product specifications. 2, centering of natural process variation, and 3, the range or spread of the variation. Note that processes must have eliminated all special cause variation in order to measure process capability. If there is still an assignable cause of variation in the system, it must be fixed prior to measuring the process capability. It would not be accurate to measure process capability of an olefins unit, for example, if the furnace was not operating properly due to a contamination issue from unusual feedstock. Measurement of process capability. Since CP is a ratio, the value of 1.0 means the process is operating exactly within its capability. In other words, a value of 1.0 means that the natural statistical variation of the system exactly matches the engineering specifications. Normally, companies will take a conservative approach and target a process capability of at least 1.5. Based on the formula presented here then, a process capability of 1.5 means that the engineering or sales specifications are wider than the range of the normal variation of the process. This is represented by figure 19.2a in your textbook, for example. A situation may occur in which the process cannot achieve statistical requirements. The process capability in this case would be less than 1, since the normal variation would fall outside the range of actual values. Such processes cannot be fixed simply by changing process variables. Instead, a fundamental change must be made to the engineering design of the system. Finally, the centering of the natural process variation should be centered within the engineering specifications also. When the process is operating with more values at the lower end of the spec than at the higher end, the process is not operating within normal variation. This would result in a process capability graph like figure 19.2D in your textbook. Remember that if CP is equal to 1.0, it is capable of meeting specifications exactly. When CP is greater than 1.0, then the process is exceeding statistical requirements. And if CP is less than 1.0, the process is failing to meet engineering specifications. Problems addressed by process capability. Process capability studies can address a wide range of quality and other issues that may arise in a petrochemical facility. Here are just a few quality concerns that can be solved through the proper application of statistical process control and process capability methodologies. Reduce or eliminate the defects from operations. Stabilize product quality. Improve product distribution for sales. Prevent poor raw materials from entering the process. Reduce over-control of the process. Reduce or eliminate scrap, repair, and rework. And improved schedule performance. The advantages of quality. During this course, we've learned a lot about quality, the reasons why total quality management has become important to American manufacturers, what defines quality to a customer, and how to determine whether a process is delivering a consistent quality outcome. Some of the important concepts of quality control include the following. Quality is an ongoing process. People, not things, allow quality results to be achieved. The definition of quality is based on external customer satisfaction. Benefits of quality are measurable: increased customer satisfaction, decreased rework, and reduced costs. And finally, quality management results in improved financial performance for companies. There are two types of quality that management builds into a system: operational quality and organizational or environmental quality. Operational quality means that processes are designed to prevent errors and deliver high-quality products and services. Organizational quality empowers workers to support their ability to enhance quality performance. Quality is created through systems. ISO 9000 offers an internationally accepted framework in which companies voluntarily comply. TQM, or Total Quality Management, combines processes, procedures, and policies within a firm to enhance customer focus, deliver continuous improvement, or Kaizen, and make decisions based on data and facts, and finally, to empower employees. In summary, quality depends on the workers who run the equipment. Management must provide the organizational support that empowers employees to solve problems and strive for continuous improvement. Some of the tools that process technicians will use for quality management include teamwork, statistical process control, as well as a variety of charts and graphs. A process that demonstrates capability is one that meets the engineering and statistical requirements. And finally, as we learned early on and have stressed throughout the course, quality depends on customer satisfaction. Thanks for listening to the lecture for Chapter 19 and for participating actively in Quality Principles PTAC 2314 at San Jacinto College. Have a great day.